Oh, hi, good afternoon. Okay, can you hear me?
Yes, Professor.
Okay, good. All right. So looks like we have a small audience now. I guess I will go ahead and start our lecture. Today's lecture is recorded. Whenever I use Zoom, recording will be done automatically. So anyone who is late or cannot attend today's lecture, they can view the recording later. But some students ask me whether every lecture will be recorded. The answer is no. Okay, so it's already answered in FAQs because the recording, if I present, if I give my lectures in person, then there will be no recording. Okay, so if it's virtual, just like what we do today, then recording will be made. Okay. Before we start, do you have any questions? All right. So then let's start our topic for today. So we are going to look at dynamic programming. So first, let's see what dynamic programming really is. It is just a programming technique. Okay, so first, let's say we look at divide and conquer. Right. So this is algorithmic technique. So you divide the problem into subproblems, you solve the subproblems and use the solutions to the subproblems, combine them to come up with a solution to the original problem, right? So that is divide and conquer. For instance, merge sort is a divide and conquer algorithm, and quick sort is also divide and conquer algorithm. So in reality, when we have a recurrence relation that express the current problem in terms of a number of subproblems, then this is called divide and conquer. All right, so that means that the second thing we do have is what we call a recurrence relation. So suppose that we have formulated a recurrence relation for solving a problem. So this of size n. Formulated, let's say that problem is called P of n. And then this P of n relies on a number of subproblems. Let's call them pk1 up to pkm, where each of these parameters ki is less than n. Hence, they are subproblems because the size of the parameter is smaller than the original problem. Okay, so then once you have a recurrence relation, then you could simply convert that recurrence relation into code, and we call that a naive recurrence or naive recursion. So the coding is straightforward, but the running time is sometimes actually you will have a exponential blow up. Okay, so let's see this using an example. So the example is straightforward. So let's look at Fibonacci numbers. So we know Fibonacci number is this. So you begin with 1 and 1. So this is a Fibonacci series. So this is the n is equal to 0. So this is n. And this is a Fibonacci number. So 1, 2, 3, 4, Okay, and then Fibonacci number is the summation of the previous two numbers when n is greater than 1. So for instance, when n is equal to 2, then this is 2 because 1 plus 1 is 2. And then when n is equal to 3, it's equal to 1 plus 2, that is 3. And then when n is equal to 4, it will be 2 plus 3, so that will be 5. And then 5 here. So that will be 8, right? 3 plus 5 is 8, and the 6 is 13. So you can go as big as you want, go to infinity. So that is Fibonacci number. And this is a recurrence relation because I use this FIB to mean P, right? So earlier we say P of n. So but now I gave a concrete meaning to this symbol P. So I use Fib, so that represents Fibonacci number. And then I have two subproblems, Fib of n minus 1 and Fib of n minus 2. So they are the same problems, right? So they do the same kinds of operations, but with smaller parameters. So this parameter is n minus 1, the other one is n minus 2. Okay, so that is a recurrence relation, and then we can quickly code this recurrence relation in Python. So that's what this next cell looks like. We define a function, Fib of n. So if n is equal to 0 or n is equal to 1, it returns 1. Otherwise, it returns the summation of the previous two Fibonacci numbers. So straightforward. So that part is a naive recursion of this recurrence relation. And then we try to run it out to see how quickly we can get these results. So we do this for n in range of 37, so which means that n will start from 0, 1, up to 37 minus 1, that's 36. And then we want to see what the numbers are. Okay, so now let's simply run it. Let me just clear up the output. And then we're going to run this. Doesn't clear it up. Clear it up. Okay, now it's clear. So now let's run it. So as you can see, for the earlier one is quick, but then beginning from n is equal to 35 to 36, that would take a while, right? So it takes a while. Now, if I do a little trick, so I'm going to talk about that trick later. So right now, this is one of the tricks that I will do. So let me go run it. And then we're going to do this. And so this is bottom up. Yep. All right. And then we're going to run this. So as you can see, I can make a very big n, right? So then this is just blink of a second. So everything is done. Okay, so what is that trick? Right, so as you can see here, right? So this n now is 180. It's just a blink of a second. I get all the results in, and earlier n is up to what, 36, and then it takes a while. So what is that trick? So that trick is called dynamic programming. Okay, so now let's look at what dynamic programming is. So first, let's do a little analysis of the naive recurrence or recursion implementation. So this is the one that's really slow. So now we start from Fib of n. Let's say this n is 36, because we know that it took a while for computing this one. So let's see why it would take a while. So in order to do this, then I'm going to compute, I need fib of 35 and need fib of 34. Okay, and then in order to do this, I need fib of 34, and then I need fib of 33. And this, again, I need fib 33, and this is, again, I need fib 32. So as you can see, this problem, fib 34, you will need up to this now, you have to compute it twice. And 33, you got to compute it twice. But as you can see here, for this 34, this is 33, you're going to see it again. You're gonna, so you got 33 here, you got 33 here, you got it 33 here, right? So then if you just keep going down, you will see, for instance, the 32 will appear many times. So you got 32 here, you got 32 here, and then you got 32, right? So then if you look at the height of the tree, so this is really, so there's a level, so 36, so each level is -1, so it's sort of a linear, but then a lot of these things, you end up recomputing them. That's why it takes time. Okay, so that's exponentially many repeatings, so that would cost time. So then once you realize this, and the immediate remedy would be, why do I record the result of the subproblems, right? So the idea then is use an array, let's call it memoiz. Okay, so I call it memo, but this is a memoization. So this is just basically, I'm going to remember the result of the subproblems, right? So this is a memo. It's a additional storage. So it's from 0, from 1, and so on, up to n minus 1, right? So if n is equal to 37, then this is 36. So what I do here is that for any particular ones, let's say I'm here, then I want to see whether this has a value. If it has a value, then I simply return that value. Otherwise, I'm going to look at my previous two values to see whether one of them has a value. Okay, so basically that's what I do. So I start, for instance, I start from 0, I start from 1, so I know there are 1 and 1 here, and then going 2. So let's say this is the first time I see it. So 1 and 1, it becomes 2, and then I go to 3. This is the first time I see it, that will become 3, and so on. So as you can see, the recurrence, the dynamic programming implementation would be for any n, if you try to compute this, I first want to see whether I have a value there. If it has a value, I simply return that value because it's already computed. Otherwise, I'm going to look for, okay, from this storage, whether I have computed the previous two. Because it's recurrence, this is a recursion, so which means if you don't have a value, then you have to continue on, okay, until you see the first one, you don't see it, and then you compute that value, and then you return that value back to this recursion call. So that means each subproblem, now this is an important message. So each subproblem is computed only once. Now, this is really important to remember. So each subproblem is computed only once. So once it's computed, the result is stored in this array called memo. So next time when you want the result from that subproblem, then you don't have to, well, you don't need to recompute it. Instead, you just do a table lookup. So that's the trick. Okay, so that's why you can have this done really quickly. And that is dynamic programming, right? So it's really not a complicated thing from this point of view. Once again, dynamic programming, you can describe it in maybe in two sentences. One is come up with a recurrence relation. That's the first sentence. The second sentence would be to use the memorization to remember the results of subproblems so that each subproblem is computed only once. Okay, so with that, then you can often speed up the computation, and that is dynamic programming. So if you look at the term dynamic programming, really it is a programming technique, right? That's why it's called programming. Actually, this term was invented before computers ever existed, right? So this in early days, without a computing device, computers, people do this kind of computation. They make up a really big piece of paper. They make a very long memo, right? So this is fill in each of these cells from the subproblems, from the smallest subproblem, and build your way up. So that's programming. So then anybody who can do arithmetic can actually carry out this thing. So without really come up with really complicated things. And the result of it is it runs fast. So let's do this again, right? So we can change, let's say I can change to a bigger number, 280. Now this is big, so maybe I don't want this big, but we can try it. Okay. So that's it. So that's done, right? So this is now. So this is the 280's Fibonacci number is this. Now this is a huge number. Okay, so this is a huge number. Right? Then we can compute these things in a blink of a second. So how much time? Now we compute everything. Now let's see, I have this time here, 18 microseconds. I compute so many things already. All right, so then you may want to know, okay, what is the complexity analysis of a dynamic programming? So it really depends on two things, right? So one is the number of subproblems. So you have to compute each subproblems once. The other one is the recurrence relations. So this is number one. Number two, let me just, sorry, let me, one. And then the number of dependencies. Number of dependencies on in the recurrence relations. Number of dependencies, let me specify of subproblems in a recurrence relation. So let's say the subproblems in our case in Fibonacci number is n. Okay, so this one is n, and then the number of dependencies is 2, Okay, so then for each subproblem, you have 2. So then altogether, what you need to do in terms of the number of computation you want to do is 3n, right? So the n, so you think of that is this dependency times n, right? Because you have this many subproblems, but each subproblem depends on 2 subproblems, right? So you got to have 2 times n many dependencies altogether. And then since you need to compute each subproblem, so the upper bound will be n plus 2n, so that's 3n. So that's upper bound, so that's linear time. That's why you see this algorithm runs fast. Okay, so memorization is done fast, and of course you can also get rid of recursion completely, and that is called bottom-up approach. So bottom-up approach, as we so this is just the other side of the same coin, right? So when you look at memorization, so you use a recursion. So you still use a recursion. So you still use recursion, but the only thing that's different is that when I call this and it has no value, then I'm going to check the previous one. If they don't have value, I'm just going to keep checking until you see the first one that has a value, right? So at the beginning, you could be just here, and then you fill their value in. The values you fill in is from the smallest parameters. So if I don't do recursion, which means that I can simply start from the smallest parameter and build my way up, right? So build my way up until you see n. So that is called bottom-up approach. So bottom means the problem with the smallest parameter. So that's the bottom. And then you increase the size of the parameters. So that's up, right? So then this is called bottom-up approach. So there is no recursion. Sometimes the people prefer this because now there is no overhead, because recursion in terms of compiler, in terms of the implementation of a calling, it has some overhead because you have to store the caller's information. Then you call the subproblems, wait for the results to be returned, and then you have to maintain a pointer there, right? So the return address. So that's overhead. If you don't even want that, then you can just get rid of this recursion at all, completely. Get rid of completely. So now this is the one. So we build from the bottom up, right? So first, I set it to n to be 240. I set a memo. Again, it's a memo. So this is 240 long. And then from the bottom up, that's what I'm start from the bottom. So memo of 0, memo 1, they be 1. And then for I from 2 to n minus 1, I just add the previous 2. So that is bottom-up approach. So now we can run it. Same thing, just 18 microseconds, then you get all of this done, right? So, okay, so the overhead doesn't really play much damage in this case, but sometimes you want to cut down that overhead if you want. Okay, any questions on this? All right, so that gives you an idea what a recurrence relation would be and how to solve it using dynamic programming. So as we want to do more, right? So we want to analyze it more. So then the actual difficulty is not the dynamic programming itself, is how to come up with a recurrence relation. So now let's look at dynamic programming. So we know what it is. We also know the running time of dynamic programming depends on two things. One is the total number of different subproblems. The other one is the number of dependencies of subproblems in your current recurrence relation. Okay, so that is the complexity analysis of it. But then the most important part is the first thing is to come up with a recurrence relation. So how to come up with a recurrence relation. So I'm going to spend probably not probably, I plan to spend 2 weeks, well, actually this week and the next week, to give you lots of different examples and try to give you an ideas how a recurrence relation can be formulated. Okay, so that is actually when people talk about dynamic programming, that is the thing that they concern. Once you have a recurrence relation, then using memorization is a standard approach. So that is a programming approach. So for that, let's look at change to my slides. Oh, by the way, all these teaching materials are available here. Okay, so this is week 1. Go to week 1. So here, so the introduction to dynamic programming, the one you just saw, Fibonacci numbers, and then this is the PDF dynamic programming I just opened. And after we look at how we can formulate what general approach we use to formulate a recurrence relation, then we are going to look at rod cutting. And that will be the second example we're going to look at. After that, we're going to look at robot coin collection problem that I think in your homework assignment, sorry, not homework, in your coding assignment, you will need to implement robot coin collectors. So we're going to talk about that later. All right, so now let's just look at so we already seen this. Okay, so this is the slides I'm gonna focus on. So formulation and the so this is a coin collector. So this is not the slide. Here's a slide. Okay, tricks to obtain a recurrence relation. So this part, as I said, is the most important part of dynamic programming, and sometimes it is also the most difficult part. So that you will need mathematical training. So then, of course, I here provide you what I think would be tricks, because that works for me. So if you talk to different people, they may have different ways of looking at it, but this is my way to look at it. So I sort of look at this recurrence relation design in 2 phases. The first phase is I'm going to come up with a formulation of the problem. So this formulation is really just a naming formulation. So naming, all right? So naming formulation means 2 things. One is the name of the problem. You would want to use some kind of name that gives you an intuitive sense, right? So when you look at the name, for instance, the FIB we use, that represents the Fibonacci number. So that is a name. And then the second is parameters. Second part of it is parameters. You gotta determine what parameters you are going to use to represent your problems. So that part is called naming. All right, so this is the first part. Interpret and formulate the problem by specifying parameters, where parameters represent the size of the problem, either original problem or subproblems, because they are the same problem, just the size of the parameters are different. So that is divide and conquer, right? So they are the they are the same problems, but they are subproblems because they work on parameters of smaller size. And then we're going to come up with a recurrence relation. So that I call localization. Now, once you have this done, then you can simply concentrate yourself on the parameters and you see whether you can find subproblems so that these the original problem would depend on. So that's what I call localization. So what that means is for a given subproblem, which is specified by parameters, and we want to figure out how it is affected by smaller subproblems, which are also specified by parameters. And then we simply express this dependency as a recurrence relation. That is the final outcome of this analysis. Once you have that, then you use a memoization technique. So that's a standard technique to solve it. And that is dynamic programming, right? So that is dynamic programming. Of course, if you don't want to use recurrence relation, then you can get rid of it by filling out that table memo from bottom up without using recurrence relation. But using recurrence relation, the good thing about it is coding is straightforward with a trade-off of a little overhead, right? But that is not exponential trade-off. It's just little overhead, not a whole lot. All right, so now let's look at another example. And I try to use an example to explain these two things I call tricks to obtain a recurrence relation. And this works for me. You can find out your own way to see which one works for you better. So now let's look at this rod cutting problem. So that's a Python code. So now let's first look at what is the problem is. Of course, if you look at your textbook, and then of course you can come up with a nicer story. But if we get rid of that story, what is the things here is the following. So let me open up a whiteboard. Okay. So rod cutting is this. Let's say I have a rod. Maybe iron rod or steel rod, whatever, right? Okay, maybe originally it is a long length. So let's just do the measure by length, LEN. So let's do the measure by inches. So n inches. Okay, so now the problem here is this. I will pay certain amount of money for P of n. And then when I sell it, I get a sales price. Let's say I subtract the money I pay to get it from the selling price, and I get a profit. So I get a profit. So this is a profit. So suppose you are a store owner and that you have this issue, and then you also know that cutting a rod needs some work, and also people don't need a long rod. So in reality, you are going to cut them and sell them. So maybe you cut it into, say, 1 inch and then maybe 2 inches, maybe 3 inches, and then in general, you get I inches. So then you do a market analysis, then you will know, okay, I get P of 1. I can make, if I cut this rod into 1 inch long, I can sell it for this much amount of money. And P of 2, blah, blah, blah. And then up to P of n. Of course, if you don't have anything, then actually you have P of 0. So that means you don't make profit by selling nothing. Right? So, but for completeness of a mathematics analysis, you want to include this called the boundary condition. So this is my boundary condition. Let's say I have this table. So these could be, so these numbers, it could be, you don't really have any sense of it because this is from your market analysis and depending on demands. Then sometimes maybe P of 2, even though you have a longer material, but P of 2 may be smaller than P of 1, and so on, right? So even P of n may be smaller than a shorter length because shorter lengths people prefer, and also, I don't know. So this is for some reasons, right? So so this is your input. And what's your output? Well, output is obviously I want to make the maximum profit. By figuring out how to cut that rod. Okay, so that is optimization problem. So as a matter of fact, dynamic programming is typically used to solve optimization problem. So for this kind of problem, we basically have two things we want to know. One is, so we want to know, the first thing is the maximum profit available. So maximum profit we can achieve or achievable. So let me just say achievable. So we cut it into two parts, achievable. And then the second is the actual cut or the actual solution to achieve the maximum solution. So in this case, it's the maximum profit. Okay, so that's what we want to do. So remember, once again, what we do here is we want to do formulation. Okay, and then the formulation would be rod cutting. So maybe I can use R to indicate rod, or if you want to use RC, that's fine. That means rod cutting, but it's a little bit cumbersome. So I'm just use R to indicate this is rod cutting. Oops. And then you got to do a parameters. Well, let's use maybe I, right? So this is a cutting point at the i's inches, and then you are going to do the localization. That means the current problem, how this current problem depends on, so you have this, say this is n, you have how many subproblems you're going to have. So you got to have, this is one subproblem. And so So let's say I remember I select this cut here, and then the subproblems would be the remaining one. So let's say this is 1. So that is n minus 1, right? So if you do this here, and then the subproblem this will be n minus 2. So then, of course, for given n, you have n minus 1, actually n, including itself, you have n subproblems. So then your R of n will be so these cutting point could be anything. So you want to select the one that gives you the maximum results, right? So basically, that's what we are going to come up with. So now let me move back to the things I can run. So now let's go back to my Python code. All right, so that is my recurrence relation. So R of I will be, so how many different cuts you have. So it's a J from 1 to I. So this is how you're going to cut them. So for each cut, this is R of I. So for each cut J, so say I pick a cut. So the profit will be P of J, because you can sell this part for P of J profit, and then the remaining part. Okay, so let's say this R indicates the maximum profit I can make by having a rod of I inches long. So which means the remaining one will be I minus J, right? So this part is I minus J. So the formulation out of I is the maximum profit achievable by or maybe with a rod of length I. So then the original, then you want to, because you are given a rod of length n, so what you want to do is to solve R of n. So basically what you want to solve, R of n. But then you gotta need to look for how many cuts you have, right? So this is J. J could be from 1, could be 2, could be you don't cut it at all. So which means that you got to come up with this many. So this many sub problems, and then I want to pick the one that gives me the maximum profit. So that's why then I'm going to put a max of it. So this is the maximum profit I want to make. I don't know which one. I got to try them or. So then J is from 1 to 3. This is I here. So J is from 1 to I. So that's what I have. So PJ plus R of I minus J when I is greater than 0. When I is equal to 0, that means you have no rod to sell. You sell them more. Then the profit you make is 0.
I had a question, Professor.
Yeah.
Why can you directly take the profit of the left-hand part, P of J, versus that?
You have a P of J.
Yeah, I'm saying it feels like it should be its own sub-problem as well that you dive into, right? R of J.
Okay, so you can either do out of the same thing, right? So you either you start from the left or you start from the right. You want one to show you actually can make profit. The other one will be your subproblems, right?
Yeah, and I guess you probably cover all permutations by only having one sub problem at each step.
Right. You can start from the right, so that means I'm going to cut it from, this is 1 from the right and then from the left and so on. So that is the same thing, right?
Yeah, and conceivably, if you cut at the 2 point, right, and I don't know, you have length 4 and you cut at 2 point, you have two lengths 2. You could you could dive into both of those sub problems to maximize them. But
yeah.
Yeah.
So that's one thing. The other thing is that you want to cut down the number of subproblems as much as you can. You don't want to maintain 2 R's, right? So you don't want to say R of J plus R of I minus J. You could do that, but it will not be as efficient.
Yeah.
Because you have a subproblem here, you have a subproblem here. I don't want this to be subproblem. I want it to be done because I know this sells this much.
Yeah, and I assume it still comes out to the maximum, right? If you had like a P of 2 versus an R of 2, you didn't have to dive further into the 2, provided you dive into the other side of it. Okay.
Yeah, exactly. Yeah. Good. Okay. So that's one example. So then you want to do the analysis. What would be the running time of this algorithm using dynamic programming? So as I said earlier, first we look at the number of subproblems. The other one is the relations, the number of dependencies in your recurrence relation. So the first one, we get the total number of subproblem is n. When you have a rod of length n. The second, when you have any j, actually any I, the number of subproblems is I, actually, right? So you got to have, well, I minus 1. That is more or less just I. So you have I minus 1 subproblems. And then, as you can see here, what I'm going to add up, now the running time will be you start from 1, you add 2, because you get it for each I, you got to look at I minus 1 different subproblems. Okay, so that means you start from 1, 2, plus up to n minus 1. Okay, so that's basically it, right? So this is when your input is n, so you have to look at n minus 1 subproblems. And then the here is your n minus 1, your subproblem n minus 1. Then you gotta look at n minus 2 subproblems of this subproblem. Since you remember the solutions to the subproblem, so you only compute each subproblem once. So that is your running time. With a constant, so we put a big O there. Okay, so now you got to add this one up. So how do you add these things up? So let me give you a quick trick, right? So let's say I want to add s 1 plus 2 plus up to m. So so we want to get a closed form. Closed form means that you get rid of this dot, right? It's just closed form. So the way to do this is because the summation is commutative, so I can change the order into this way. So then I'm going to add them at both sides. So the left-hand side is 2 times s. The right-hand side, you look at each column. So each column is m plus 1. And then you have m columns. So you get rid of the dot. So then is s is really equal to m times m plus 1 over 2. Now, this is a quick, so you can remember this or remember the method that I come up with this closed form. And then now my m is n minus 1. So that means the runtime in this case is n minus 1 times n over 2. So this is a big O of n squared. So this is a quadratic algorithm. All right. So that is the dynamic approach. Okay, so and this I provide you with a complexity analysis of a straight implementation, which means that you don't remember the results to subproblems, and that will be exponential. So you can just take a look by we can use a mathematical induction. So it's a pretty straightforward. So now let's run this thing. All right, so we run this. Now this is a cut rod. This is a straightforward or naive implementation. So let's run this. And now this is just run that out, this function cut rod. Now this is direct implementation of this without using memorization. So this is your textbook example, but its input so small that you probably don't see any difference at all by naked eye. So now let's make it a little larger. So what I do is I look at I from 2 to 26, and then my then I generate these random numbers. So this is a generate pseudo random number numbers between 10 and 10 times I. So I would be from 2 up to 25. So that means that you got 24. I think it's a 24 long. So this n, right? So we can run it. So this is a P. So that's what my P is. So you see what is the N is. N 25. Okay, so here 20. So starting from 2 up to 25, yeah, that's 24, right? 25, sorry. 2 up to 25, but including 2, right? So that's 25. Okay, so now we will run this without using dynamic programming, which is here. Cut rod. Okay, now just get some idea. Still running, right? So it's still killed. Now the result comes up. And then using dynamic programming, using memorization. So that's what I use here. So basically the technique is the same, the recurrence relation is the same, except that you add a extra storage. Remember the results of a previous problem. So at the beginning, you can say that all this memo for any I is equal to 0. This is the initial. And then after that, if you have something, there's a profit greater than 0, you put that value in. So the recurrence here is the same, okay, but I use a memo. So that gives you a dynamic programming approach. So now let me run this. And I run that. Okay, it's the same thing. This one is even bigger. So 28, right? Before the 26. So I run this bigger. So if I want to okay, so now I'm going to run memo. Now this is slightly bigger. You see how quick it can be done. Oops. Yeah, I want to run this one. So that's 3 and 38. So it's quick, right? So once you click, the result comes up. Okay, so if we want to now this is a randomly generated. So next time you're going to have a different. You are going to have. Hold on, let me do this again. So this is a P. This is a random. Okay, so now I generate. Oh, sorry, this is still running here. I clicked the wrong thing. Let me kill them. Start over. Okay. Now this is a cut rod is the naive implementation. I generate my instance. So that's my event instance. And then I do dynamic programming using memoization. Okay, I'm not going to do this again. So instead, now let's do cut rod. This is naive implementation. So you gotta wait. Okay, so this is 324, that's done, so it takes a while. Now I use memoization. Let's see what happened. So click the second, I click it, then the result comes up, 322. So this is n, the reason is, well, we know it's a quadratic time, but since n is not that big, it's only 25, so you don't see much difference. So if n is larger, then you'll see difference. But this is a 2 to the n, 2 to the 25, actually, it takes a little while, right, to see the results. And then you also want to know for each cut, my profit, so that is stored in the memo. So which is cut, for each cut, right? So what profit I can make for that particular instance. So that gives you the intermediate results. So the bottom-up approach would be I get rid of the recursion completely. So in other words, I'm going to start from the bottom by looking at the parameter size from 1 and then 2 and then 3 and then 4 and so on. That builds my way up. So this is the code here. So I'm not going to go through that. And then the next. So we solved the first one. So this is the maximum profit achievable. The other one is I want to know where the cut is. So this part only gives me the profit I can make by looking at the each cut. But then for the particular n, I want to know how we are going to cut these things to get my profit, which is 324. Right, so where does 324 comes up? So here it doesn't tell me, right? So then I need to remember each selection. So remember, this is the cut here. For each I is a max of P of J plus R of I minus J, and then J from 1 to I. So of course, I remember I0, that gives me the maximum value for each I. I need to remember this value. So I put that value into a different array. Let's call it C, or let's call it cut, right? So that I remember that cut. And that's what is done here. And here I use S, that means the solution. I remember the solution. So because you are comparing many different things, so I need to compare each one, then I only store the largest one in my S. So that's what we do here. So this is a linear comparison. So for I here, if Q is less than this, then I put that value into Q. Now remember, I need to remember this I. So this I will get changed if a larger value comes up. So then when this loop is done, then I know where that cut is. Okay, so basically that's how you get that cut. All right, so let's run this. And run this. And run that. And then print. Right here. So this is what I just print. Okay, so this is, I think this is the one in your textbook. And that gives you the cut. All right, so I already mentioned this. So that is dynamic programming. So I hope that after you saw this, you have an idea what dynamic programming is about. Now, once again, first, it needs to come up with a recurrence relation. And then second, you simply use a memoization if you don't care about whether you are allowed to use recursion at all or not. So that's a standard technique, using an extra storage to store solutions to subproblems. And then if you want to get rid of the recursion, you can use a bottom-up approach, right? So that's the first level of dynamic programming. And then the second level will be how to come up with a recurrence relation. So I talk about a trick that works for me. So which means that you first come up with a naming formulation, right? So formulate the problem. So you got a name, and then you got either one parameter or two parameters or more than two parameters, right? So when the problems become more involved, then you got to have more parameters, but the idea would be the same. So that's the second level. And the third level is analysis of running time. So which means that you look at two things. One is the total number of different subproblems. And then the second thing would be we look at the localization, the recurrence relations. So how many dependencies? So usually the recurrence relation will only depend either a constant number of subproblems or linearly many, or maybe even polynomially many, as long as, of course, your total number of different subproblems are polynomially bounded. Okay, that's important, right? Then your dynamic programming will give you polynomial time algorithm, because it's not going to be much more than the number of subproblems, right? So that is the general approach. Now let's look at one more problem that is called the coin collector problem. So let's go back to my slides. Okay, coin collecting robot, coin collector. So the idea is this. So let me open up a whiteboard. All right. So let's say I have a robot. Well, a human-like robot, maybe. Okay, and then you are given a checkerboard, M by N, Okay, so then each of these square will maybe you have some items in it. And now we just say I put a coin in there. So you may have a coin here. And maybe you have a coin here. And maybe you have a coin here. And so on. Or maybe you have a coin here. Okay. So what you want to do is that this robot has this input, has this checkerboard, and also has this the location of these coins. And what this robot wants to figure out is it can only follow a certain restrictions of how you can move, right? So robot has restrictions. How to move. So then what you want to do is you figure out a way, right, from the top row to the bottom row, depending on what your restrictions are. Sometimes you may say, okay, you can only start from here. You can only end up here, or you can start from anywhere in the first row. You can end up anywhere in the last row. And you want to figure out a way to pick up the most number of coins. So that is robot, I'm sorry, coin collecting robot or coin collector problem. So let me now move back to. All right. So let's see the restrictions of movement. Here, the robot must stop in the bottom right corner of the board. And the robot can move at most one cell right. Okay, so a robot here can move one cell right. And one cell down in a single step. So which means that you can either move to the right. Well, this is right means the way I look at it, not from the robot's point of view. Right? So this is the way I look at it. And not the robot right. So that's what it is. If a robot's right, just means that you can either move here, that's the right, and move down. So down is the same. The right depends on whether from my point of view or from the robot's point of view. Here, I'm thinking this is from my point of view. So you're going to do that. And then from the beginning, and this is the left-hand corner of the board. So this upper left-hand corner, so which means that you are going to from here, from my side, so that's left, on my side. So you got to start from here and end up here. And each step, you can either move to the right or move left. So that's it, right? So once you, for instance, if you are stubborn, you have lots of coins here, you keep on doing, you can always do this. And then you can, only way you can do is going down, because if you have lots of coins somewhere, then you gotta let them go. Right? So you gotta figure out a way along that route, you pick up the most coins possible. So that's the problem. So this problem turns out you can come up with a recurrence relation. So to do that, so first let's name this problem. So this is a coin collector. So then we use a CC. And I and J, so because your parameter is two-dimensional, so that means that I have to specify which cell. So this is I, or which is square, so this is J. So that is IJ. Okay, so now we want to know, we first want to figure out the maximum number of coins achievable. So we let CC of IJ denote the largest number of coins the robot can collect when it visits cell, when it visits this. Okay, so when it visits that. So that means, so we start from here at the end. What I want to find is a CC of MN. So because this is the last one. So what I want to do is do this. So how many subproblems do I have? Of course, I have m times n, many subproblems, right? So because you're looking at each of these things, you got how many? You got m times n, many different subproblems. So that's a naming formulation. The second is the dependency, or dependency means you focus on the current parameters now. You don't worry about any other parameters. So that really means localization. You don't have to look at too many things. So here, localization is only two things, because either you can move to the right, and you can either move
downward.
Down, right. So once you reach ij, so which means that you either come up from here, right, or you come up from its left. So two ways. So either you so two possible ways. So you either come up from above, or you either come up from left. So that's two subproblems. So you look at this one subproblem, the other subproblem. So you can only choose one of those, and then plus Cij. So Cij is coined. You can actually put a value in it, but now you can make it, okay, Cij is equal to 1 if ij has a coin, otherwise it's 0. But you can actually put a coin value and change the problem to collect the maximum value of the coins, not just the maximum number of coins. So that's pretty straightforward. So let's just do a Cij, and that's it. So you'll find the maximum of these two possible ways to come down to ij, plus this one, the Cij, whether it has a coin or whether it doesn't. So it has one that Cij is equal to 1, otherwise it's 0. Or if you actually place a face value on the coins, you actually collect its values, and then you change the problem to get the maximum value along the path. Okay, so that is the formulation. Okay, somebody raised a question. Oh.
I was just saying another way,
yeah, use a self, yeah, you can do that too, yeah. All right, so then the standard technique of memorization, and of course, as the memo ij at the beginning, you can put it into a value. In this case, it could just be safe to put it as 0 or a negative value, whatever. It just means that you haven't been visited. So in general, we use upside down T to indicate that it has not been defined yet. And if it has been defined, that means I have a value, I return that. Otherwise, I simply use the recurrence relation, right? You see that this is the recurrence relation. But then you have to compute that V, remember that value, and place that value at the end into that memo, because now I have a value. All right, computing time. So the number of subproblems M and M times N, and the localization dependency is only 2. So that's a constant. So that means really just 2 times M times N. So that is a constant times M times M. So that means the complexity is just M times N. And that is that problem. And then I have, okay, 1 more minute and the class is over. So now you can quickly go to, oops, week 1, CA1, okay? So you're gonna write a Python program to implement the coin collecting robot program using dynamic programming on a checkerboard, M times N checkerboard. Your program should return a pass for the robot, the same thing, right? But then I think there's different restrictions here. In a single step, the robot can move at most 1 cell east, or 1 cell south, or 1 cell southwest. So you got 3 different ways to move your robot rather than just one way. And you must stop. Okay, you can start from any position in the top row and must stop at the lower left corner. Okay, so then you figure out a recurrence relation and then plug this one in and then to figure out. So this is a concrete map that you are given. So 1 means it has a coin, 0 means it doesn't have a coin. So you have everything you need to do this coding assignment. My time is up. Any question? Okay, the question here for the homework assignments for multiple choice question, if I get one option correct, the other incorrect, do we get partial credit? Well, you get partial credit for the correct one. But remember, this is if it's a multiple answer, the wrong choice suffers a negative, suffers a punishment. So if you get one correct and one incorrect, then it cancels each other. But if it's a multiple choice, there's only one answer, then yeah, you get partial credit. That makes sense? All right. Any other questions?
No, thank you, Professor.
Yeah. Okay, then. All right, I will see you on Wednesday. Hopefully now we can meet in person this time. Okay, bye-bye now.
I have one question.
Okay, go ahead.
For the dynamic programming code you did earlier, do you have like those documents to like download and like so we could do it ourselves?
Yeah, it's all in here. So this is the code. So this is the code you can download. Rod cutting you can download. That makes sense? Yeah.
And then I guess like also would in the other video that you made to like download the software and everything, that the last couple of code problems, are those also saved?
Those are in here. So I don't know whether you actually visit. Oh, that's week 0. Everything is here. Okay, so you go to quick intro. You go Python Essential 1. You ask for this. So these are all the notebook file that you can download.
Okay.
Yeah.
Okay.
It's here. Everything you have is there. Okay.
Okay. Thank you.
All right. Okay, I guess I need to run because I have a class next in maybe in 5 minutes. Okay, so I need to go. All right, so see you on Wednesday.